Hi everyone, this is Jiong. Today we are going to talk about engineering an efficient PB-XOR solver. This is a joint work with Kuldeep and Meel. We are from National University of Singapore. In this talk, we are going to present an efficient set solver capable of handling PB and XOR constraints. Built on PB-XOR solver, we present an efficient PB model counter, which is a new state-of-art to verify binarized neural network. When you look at the title, the first question is, what is exactly PB and XOR? Now let's first look at PB. PB is short for Boolean constraint. Here we give the formal definitions of PB constraint. You can think of PB constraint as a 0-1 integer inequality. All coefficients Wi are integer constants. The right-hand side B, which we call degree, is an integer constant. Li denotes a literal. It can be a variable xi or negated xi. Each xi is a Boolean variable which can be assigned false or true. For instance, x1 plus 2x2 minus x3 greater than or equal to 2 is a PB constraint. It contains variable x1, x2, and x3. The three coefficients are 1, 2, and minus 1 respectively. The degree is 2. We all know that currently SynF is widely used. So a common question is, why do we need PB constraints? What can we benefit from the PB constraints? The answer is succinct. Succinctness is an important property of PB constraints compared to clauses. A PB constraint is usually equivalent to polynomial many clauses. For example, x1 plus x2 plus x3 greater than or equal to 2 is equivalent to the following 4 clauses. Because of the succinct representation, reasoning over PB constraints is known to be exponentially stronger than resolution on clauses. Another good property of PB constraint is being compatible. For example, a clause can be represented by an equivalent PB constraint. See, x1 or x2 or x3 is equivalent to x1 plus x2 plus x3 greater than or equal to 1. Also, a cardinality constraint can be represented by a PB constraint. For example, x1 plus x2 plus x3 greater than 2 is a cardinality constraint in PB format. What's more, a neuron in binarized neural network, the sum of Wi, xi greater than or equal to b can be represented by a PB constraint. Therefore, PB constraints have an extensive applications. Remember, our topic is PB-XOR solving. So next, let's talk about XOR. XOR is short for exclusive or constraint. We give the formal definition as follows. The symbol circle plus represents addition in the field of 2. Each xi is a Boolean variable which can be assigned either false or true. The right-hand side degree is a Boolean constant. For example, x1 XOR x2 equals 1 is an XOR constraint. XOR constraints have many good mathematical properties, and they are widely used in a lot of techniques or applications. In the following slides, we present an application of interest, approximate model counting, to showcase the importance to solve XOR constraints. Before jumping to approximate model counting, let me briefly introduce the notation of model counting. Suppose we have a formula f over Boolean variables x1, x2 until xn. A solution is an assignment which makes the formula f evaluate to true. We use SO of f to denote the set of solutions of f. A classical problem called satisfiability is to determine the solution set is non-empty or not. The problem model counting is to compute the size of solution set. For example, given a formula x1 plus x2 is greater than or equal to 1, the formula has 3 solutions, 1, 0, 0, 1, and 1, 1. For instance, assigning 1 to x1 and 0 to x2 can make the formula evaluate to true. Therefore, the formula is satisfiable because the solution set is not empty, and model count is 3. That is the size of solution set. However, exact model counting is known to be Sharp-P complete. That is first proposed by Valiant in 1979. In recent years, there is a rise of approximate model counting, which is much more scalable than exact model counting. Approximate model counting takes as input a formula F, a tolerance epsilon, and a confidence delta. It aims to return a count C such that the count satisfies probably approximate correct guarantees as shown below. The algorithm works in the following way. Suppose the ellipse below represents the solution space, and the black points inside represent solution. In most cases, the number of solutions is too large to enumerate all the solutions. Therefore, at first, we use a set of XOR constraints to partition the space into roughly equal cells. Then, we invoke a set solver to enumerate solutions inside a cell. Finally, we multiply the number of solutions inside the cell and the number of cells to get the estimate of exact count. Now, let's see how to perform approximate model counting on a PB formula. Suppose we have a PB formula F. As we partition the space into cells, a set of XOR constraints are added to F one by one until the cell is small enough to count solutions. We use F prime to denote the formula F conjuncted with XOR constraints. Then we enumerate solutions of F prime to compute the number of solutions within the cell. Here, we are faced with the problem to solve formula F prime, which is a conjunction of PB constraints and XOR constraints. We use PB-XOR to denote this kind of formula. Once we solve the PB-XOR formula F prime, we can estimate the count by multiplying the set of F prime and the number of cells. Therefore, we need an efficient solver to solve the PB-XOR formula. In general, there are two approaches to solving PB-XOR formula. Firstly, we can encode PB constraints into SYNF, thereby transfer PB-XOR formula to SYNF XOR formula and use SYNF XOR solver to solve it. However, encoding PB-XOR to SYNF XOR formula will enlarge the set of the formula, and we cannot benefit from PB solving techniques either. Another approach is to solve the PB-XOR formula directly by PB-XOR solver. However, there is no PB-XOR solver available right now. In this work, we propose the first PB-XOR solver, LimPB. It enables a set solver to benefit from the powerful PB solving techniques and can handle XOR constraints efficiently by Gauss-Jordan elimination. The solver also can coordinate PB solving and XOR solving well. Finally, we will empirically show PB-XOR solver is more efficient than SYNF XOR solver to handle PB-XOR formula. The slide shows the framework of a PB-XOR solver. Remember that GJE is short for Gauss-Jordan elimination. We can see a PB-XOR solver consists of a PB solver and a GJE component. The PB solver is used to handle PB constraints, while GJE component is designed to handle XOR constraints. In this way, on the one hand, we can reuse current PB solving techniques. On the other, we can perform Gauss-Jordan elimination to solve XOR constraints. Then, the most important task now is how to efficiently coordinate the PB solver and Gauss-Jordan elimination. At first, we propose to sequentially connect the two components. As we start to perform propagations, the PB solver firstly propagates over PB constraints until there is no more propagations left. Then we start to run Gauss-Jordan elimination to propagate over XOR constraints. However, this approach may cause a delay to update the assignment of variables in XOR constraints. Let me show you an example. Suppose we are going to solve the following PB-XOR formula. The first PB constraint is negative x1 greater than or equal to 1. The second is x1 plus negative x2 greater than or equal to 1, until we have xn and xn plus 1. XOR constraints have x1, XOR x2, XOR x3 equals 1, until xm, xm plus 1, and xm plus 2. We use the red color to highlight the variables evaluated to be true, and the blue color for variables evaluated to be false. Now let's try to solve the formula. We start to propagate over PB constraints. From the first constraints, we know that x1 is false. Once x1 is false, from the second constraint, we can infer x2 is false. Similarly, we know that all the variables are false. Then we propagate over XOR constraints. In the first constraint of XOR, we get a conflict because all the X are false. The right-hand side should be 0, not 1. We find that the conflict only involves variable x1, x2, and x3. It means most propagations of xi with I greater than 3 are useless. If we can update the assignments of variables in XOR constraints early, the solver can detect the conflict after x3 is assigned and avoid the useless propagations from PB constraints. Therefore, we propose a synchronized approach to connect PB solver and GGE. This time, the two components start at the same time and synchronize the assignment of variables until the end of the propagation. Let me show the process using the same example. Once we get the assignment of x1 from PB constraints, we immediately update x1 in XOR constraints. Then we get the assignment of x2 from PB and update x2 in XOR. Finally, after we get the assignment of x3, we reach the same conflict in XOR constraints as before, but we don't have to perform many useless propagations from x3 to xn in PB constraints. That saves much time for us. Empirically, synchronizing PB solver and GGE indeed saves us time compared to sequential connection. However, in practice, it introduced a lot of overhead when frequently switching between PB solver and GGE. Then we propose another approach to improve the sequential connection. This time, we transform partial XOR constraints to PB constraints. Now, the PB solver can find the potential conflict in XOR constraints early. For example, if we can transfer x1 XOR x2 XOR x3 equals 1 to x1 plus x2 plus x3 greater than or equal to 1 and add it to PB solver, then the PB solver can detect the same conflict on its own. In the paper, we propose a few heuristics to select XOR constraints to be transformed and empirically present the best one. If you are interested, please refer to our paper in CP21. We show in the paper that the transform-based approach empirically outperforms the synchronized approach, and the transformation indeed reduces the overhead from synchronization. Next, we perform experiments to evaluate the performance of PB-XOR solver. We implemented a prototype of PB-XOR solver, LinPB. Built on LinPB, we implemented an approximate PB model counter, Approximate PB. We use PB model counter as a proxy to evaluate the underlying PB-XOR solver. We compared our counter with state-of-art model counters, Approx-MC4, which is built on top of SynF XOR solver, GANAC, PROG-MC, GP-MC. Experiments were conducted on 1,078 instances arising from quantitative verification of binary neural networks with respect to different properties such as robustness, Trojan attack, and fairness, provided by Valuta et al. On the top, we show the character plot for the results of prior state-of-art counters. In the figure, a point xy represents the counter can solve x benchmarks within y seconds. That is, the curve on the right means a counter can solve more benchmarks within the same time limit. Currently, Approx-MC4 performs the best. On the bottom, the table presents the number of solved benchmarks by the corresponding model counter. We can see Approx-MC4 solved 800 benchmarks, which is the current state of art. However, as shown in the table right now, Approximate PB can solve more than 900 benchmarks, which increases the prior performance by solving 110 more benchmarks. The characters plot also shows Approximate PB achieved the best performance. Furthermore, the fact that Approximate PB outperforms Approx-MC reveals that the underlying PB-XOR solver outperforms underlying SynF XOR solver. In conclusion, we presented an efficient PB-XOR solver, LinPB, in this talk. Built on top of LinPB, we presented an efficient PB model counter, Approx-MC PB. Approx-MC PB can solve 110 more instances than prior state-of-art on BNN benchmarks. The code has been published online. You can scan the QR code on the left to access the source code. Thanks for your time. Any questions?